Chapter 6, Normal Distributions. Here comes an important one. This chapter provides a key link between a number of subtopics of elementary statistics, namely the descriptive statistics that we studied in Chapter 1, 2, and 3, the probability theory that we went through in Chapter 4 and Chapter 5, and also the inferential statistics that we are to begin from Chapter 7 and continue upon until the end of the semester. They all merge right here in Chapter 6. Technically though, this is not going to be a very difficult chapter. All we have to do is to understand and utilize this table, the normal table, or more precisely speaking, the standard normal table. The picture here is an outline of a graph of something called the standard normal curve, and it is associated to a character z, so it is often called the z-curve. Same for this table. We have a bunch of numbers here, but they're all associated to a certain degree to a character z, so it is often called the z-table. Now, how do we use this standard normal table, and what do they mean? What do these numbers mean, and so on? Well, all these will be discussed in 6.2. After that, we are going to study some application problems. We are going to set up some realistic application problems regarding normal distributions and solve them using that standard normal table, which I just showed you before. 6.4 is going to be relatively a minor issue, and I'm going to just dissolve this section and then slip it, integrate it into section 2 and section 3. 6.5 is another application, normal approximation of the binomial. And we studied the binomial distribution in Chapter 5, at the end of Chapter 5, and it wasn't too difficult to begin with, but the normal approximation is actually even easier, so I don't see anybody having any difficulty there. Now let's begin. What do you mean by so-called a normal distribution? It's a kind of continuous probability distribution, as you can see from this kind of continuous curve that's going up and down, and with appropriate properties that we're going to discuss a bit later. And let's do that with my notebook here, but let's begin with a bit of review. After all, Chapter 6 is also about probability distributions, so it's a kind of continuation of Chapter 5, so let's talk about it. Alright, let's begin with something called random variable. What is so-called a random variable? The random variable is a quantitative variable that takes a unique numerical value, like payoff, for each outcome of a sample space. If you like pure mathematical expression, you can understand it kind of like this. It's a real valid function defined in a sample space. If you take even less mathematical point of view on the other side of extreme, then you can consider it as a kind of scheme to put numbers into any kinds of outcomes of sample space. For example, if you have an EARN model of something like this, and we have different colors of balls, but if you put numbers into it, then that's the random variable. Now, what is so-called probability distribution? Well, here is an attempt by our textbook authors. A probability distribution is a distribution of probabilities. Just change the order. Associated, blah, blah, blah. I don't like this kind of explanation any more than you do, so let's do it my way. Let's talk about so-called the discrete random variable. Discrete random variable is a random variable that takes only discrete set of values, like finitely many sets, or like all the integers and things like those. And the probability distribution of so-called, the probability distribution of discrete random variable is at a combination of two functions, so-called the probability mass function and the probability, cumulative distribution function. I think I'd better start all over. A probability distribution of a discrete random variable is its probability mass function, PMF, and the cumulative distribution function, CDF, put together. And then we talk about PMF and CDF. It turns out, by the way, you don't really need both of them to have full knowledge of the probability distribution function, to tell the truth. Because if you know the PMF, you can find out CDF, and vice versa. If you know CDF, then you can find out PMF. What are the relations? Well, as you can see, the PMF consists of a bunch of x values, and then the probabilities associated to those. And how about CDF? Those x values with non-zero probabilities of this PMF, also those x values are the breaking points, the discontinuity value of this cumulative distribution function. And then you have a bunch of step functions where you just add up all those probabilities before that. So you have cumulative probability. So we have steady increase from 0 all the way up to 1. And we have this step-by-step function. And then the size of each jump of each step is the probability mass. So you can get CDF from PMF and also vice versa from CDF to PMF. We did those kind of exercises a lot in chapter 5. In other words, if you know any one of this PMF or CDF, then you can say, I know all about the probability distribution of that discrete random variable. Remember this, please, because if you move on to continuous random variable, we are not going to use PMF. We will still use CDF, but in place of PMF, we're going to get something else. Okay. Now let's talk about expected value. And expected value is obtained by simply multiplying all those x values and the probability mass and then add them together. Here is an example. Next, the variance. Instead of multiplying x and the probability mass, multiply the deviation squared and then the probability mass. And then add them all up. Here's an example. That's called the variance. Variance measures kind of dispersion, how far apart those likely values are. And then the standard deviation is the square root of the variance. Okay, let's go back to PMF and CDF, and let me ask you this question. What if you have not just 1, 2, 3, 4 x values for this PMF? What if you have hundreds of x values? Even worse, thousands of x values. Then the probability 1, the full probability 1 will have to be shared by those hundreds, maybe thousands of different x values. So each height, the height of each dot will be very, very small individually. So the graph of PMF looks very much like a bunch of dots really, really close to the x-axis, and then don't really mean much. Now, if you look at the cumulative distribution function, on the other hand, we have to have cumulative probability, so it grows from 0 to 1, yeah, but the jump size will become the probability mass, which are going to be very, very small because there's so many x values that share the full 1. So the jump size will become really, really small, and that can be well approximated by a continuous function that is steadily going up from 0 to 1. And that's how the discrete and continuous random variable are related, and how the continuous random variable can be used to approximate discrete random variables, kind of like, as a matter of fact, this example that we went through in 5.1. This picture, by the way, came from SAT scores, and SAT scores are all integers. But as you can see here, we are not dealing with discrete random variable, we are looking at a continuous curve. What happened? The reason is because the difference 1, the score difference of 1 is so small compared with this range from 200 to 800, it was more convenient to consider the approximation by continuous random variable. Okay, one more comment. This is a little bit advanced. Now, the CDF of continuous random variable will be a continuous function, steadily increasing from 0 to 1. Now, if you take the derivative of that, then you're going to get a positive derivative, and that function is going to be called the probability density function. Now, this is 1680, so calculus is not required as a prereq, so I cannot talk about derivative anymore. It was just the comment. But we still have to talk about continuous random variables. So what we do? Well, we have to take rather unusual step. Out of nowhere, we just bring in so-called probability density function, which is fundamentally different from the probability mass function. And we have this kind of property: x is always positive, greater than or equal to 0, and then toward infinity or negative infinity go down to 0. We can see this kind of picture, either asymptotically or physically. And number 3, the probability where the random variable takes a value between a and b is given by the area of a certain region. Underneath y equals to f of x, the graph, above the x-axis, y equal to 0, and between two vertical lines, x equals to a and x equals to b, kind of like this blue region here, or the red region over there. That area corresponds to the probability. And if you have that kind of property, yeah, you have probability density function. And if you understand the relationship between the density function and the CDF with derivative versus antiderivative, that's great. If you don't, never mind. There is another way to understand it. Here it is. The probability density function can be understood as an outline of probability histogram, which corresponds to data histogram if the probability is empirical. Do they resemble? In this picture, not really, but if I increase the class interval size, you will see semblance. See? So that's how chapter 1, 2, and 3, early part of chapter 3, those descriptive statistics part is associated to chapter 6 topic like this. The probability density function corresponds to the outline of histogram for sufficiently large class intervals. Sufficiently large class interval numbers, so class interval size will have to go down to pretty small. Now let's focus upon the normal probability distribution. By the way, the blue picture here is normal, the red one is not. And it is this kind of probability density function, or the outline of histogram, symmetric with respect to the expected value x equals to mu, and going down as we go down, as we go far away asymptotically, and we have this analytical expression. You don't have to pay too much attention to that. Instead, let's discuss how this normal curve is affected by the change of expected value and the standard deviation. If I move my mu, then the picture, this normal curve, follows it, because it's more likely that we have concentration around the expected value, so we have bigger probability density there. Symmetry with respect to x equals to mu. And now let's change the standard deviation. The bigger the standard deviation, the flatter it gets. The smaller the standard deviation, more concentration in the middle. As we said before, standard deviation measures the dispersion. So smaller standard deviation means more concentration toward the expected value. And then the bigger standard deviation means more diversified, more spread out data. So much for the introduction. In the next video, we're going to talk about the standard normal distribution and standard normal table.